Welcome to the deep dive. We're taking listener-provided material and, well, extracting the absolute core of what you need to know.
That's right.
Today, we're diving into a master's thesis examination transcript. It's all about designing a smarter way to control something called a solenoid valve. Think of this as your express lane to understanding some really clever engineering.
Exactly. We've gone through this academic presentation to pinpoint the key innovations in making these electrically controlled valves work more effectively.
Okay.
Our goal today is really to unpack this research and highlight why it's actually, quite significant.
Okay, let's unpack this then. A solenoid valve. Sounds a bit complicated, maybe, but the basic idea is simple.
Yeah, pretty straightforward.
Imagine an electrically controlled faucet, basically. You send an electrical signal, and boom, the valve opens or closes. It lets fluid flow or stops it.
Right.
Now, the control circuit, that's the brain managing that signal. The simplest version, maybe just a relay, using a small electrical nudge to control a much bigger electrical push that opens or closes the actual valve.
That's a perfect way to think about it. And this research we're looking at, it's all about making that brain much, much more efficient.
Okay.
So the central question is, what happens to the fluid flow if we don't just, give the valve full power all the time?
Right.
Specifically, the researcher looked into the impact of reducing the voltage, but doing it in steps.
Okay, so reducing voltage in steps. The research was trying to answer, what, two main things then?
Yeah, basically two key questions.
First, if we lower the voltage in stages, can we keep the flow rate, the same while using less power? That would be huge, right?
Definitely, that's the efficiency angle.
And second, if we do reduce the voltage like that, how much does the flow rate actually change? Does it drop off?
Exactly. And what's fascinating here is that you usually face a trade-off. You can often either save energy or precisely control how much fluid comes out, but getting both at the same time.
Yeah.
That's the real
Yeah.
challenge. This research dives right into how to potentially bridge that gap.
And to explore that, the researcher aimed to build a control circuit with some very specific abilities. What exactly did it need to do?
Well, the circuit needed to handle a few key tasks. First, obviously, it had to be able to step down the voltage supplied to the valve.
Right, the core idea.
A second, it needed to control how long the valve is initially hit with that higher voltage to get it open fully. That's called the excitation state.
Like giving it a good initial push.
Exactly like that. And third, it needed to manage the lower voltage level required to just keep the valve open after that initial push. That's the holding state.
So it's about having really fine-grained control over the power, both when it first kicks in and while it's just sort of staying open.
Precisely.
And the big reason for all this fine-tuning.
Well, by having this level of control, the aim is either to get significant energy savings or to gain the ability to really fine-tune the amount of fluid flowing through the valve. Or maybe both.
Gotcha. Okay, so before creating their own design, the researcher looked at what was already out there, right? For controlling voltage in these circuits.
Yes, they reviewed the existing tech.
What were the main solutions they found?
The presentation outlined two primary methods people were using. One involves using two separate power sources and two distinct signals.
Two of each, okay.
Yeah. One set is used for that initial excitation burst to open the valve quickly, and then a lower voltage and a different signal take over for the holding phase, just to keep it open efficiently.
Okay, like shifting gears in a car, high power to start, then cruise control.
That's a good analogy, yeah. High power gear, then an efficient cruising gear.
Okay, two power sources, two signals. Makes sense in a way. What was the other common approach?
The second common method uses just a single signal, but it relies on something called PWM.
PWM.
Pulse width modulation. Imagine flipping the full power supply on and off very, very quickly, like super fast. By changing how long it's on versus how long it's off during these rapid cycles, you can effectively control the average voltage delivered to the valve.
So it's not actually lowering the voltage source, it's just chopping it up.
Exactly. It's like quickly tapping the accelerator in your car. Short taps give less power on average than longer presses would.
Got it. Okay, so those were the existing ways. Now, this research took a slightly different path, summarizing their circuit design approach into 4 key areas leading to 3 different versions, 3 generations of their circuit.
Right. And what's really interesting is how they learned and built on each version. The third generation wasn't, a completely new invention out of the blue.
Okay.
It took the voltage stepping capabilities from the second generation and incorporated some of the simplicity of the first generation, which was basically that straightforward relay function we talked about.
Okay, merging ideas.
And the major achievement of the third generation was being able to get that step-down voltage using just a single control signal. That simplifies the whole system quite a bit.
Right, less wiring, less complexity. Okay, let's dive into the specifics of that circuit design then. What were some of the critical bits they had to figure out? The presentation mentioned the power supply, for instance.
Absolutely, that was fundamental. The specific solenoid valve they were working with needed 28 volts to operate properly.
Okay, 28 volts for the valve.
But their control circuit also needed its own power to function, which
Yeah.
they set at 15 volts.
Right, the brain needs power too. How did they get the 15 from the 28?
Well, initially they used a component called a linear regulator to step down the 28 volts to 15. Pretty common component.
But that didn't quite work out, did it? I remember reading something about it getting too hot.
Exactly right. In this situation, where there was a significant amount of power being handled, the difference between 28 and 15 volts at whatever current the circuit drew, the linear regulator got incredibly hot.
Not good.
No, and it even started providing an unstable voltage because it was overheating. It was essentially just wasting all that extra energy as heat. Very inefficient.
So what was the fix?
They switched to what's called a switched mode buck module. Now, unlike the linear regulator, which basically burns off excess energy,
Right.
the buck module rapidly switches the power on and off, much like PWM, but for power conversion, delivering only the necessary amount and wasting much, much less energy as heat. It's way more efficient, especially in higher power situations like this.
That makes a lot of sense. Less wasted energy, less heat, more stable. Okay, what about the isolation circuit? That sounds important, like for safety.
It is crucial, yeah. The purpose of the isolation circuit is basically to safeguard the more delicate and, frankly, expensive electronic parts of the control circuit from damage.
How so?
Think of it as a safety barrier. It protects against unexpected high voltage coming back from the valve side, or maybe sudden electrical surges, strike currents, that kind of thing.
Okay, and how did they build this barrier?
The researchers used light-emitting diodes, LEDs, and photoelectric transistors. The idea is really clever. The control signal is transmitted optically.
Using light.
Exactly, via light,
Yeah.
rather than through a direct electrical connection. So the control side, the low-power brain, and the load side, the high-power valve, are electrically separated.
Ah.
So if something goes wrong in the high-power side, a surge, whatever, it's much less likely to fry the sensitive control electronics on the other side of this light barrier. It's a very neat way to create a buffer.
Very clever indeed, using light as a safety net. Okay, now transistors were also key components mentioned. They used NMOS and PMOS transistors. What's the difference there, and why use both?
Right, this gets a little into the weeds of electronics, but the key difference is how they're turned on and off by the control signal.
Okay.
Think of NMOS transistors like a normal light switch. You apply higher voltage, it turns on. You apply a lower voltage, low, it turns all off. Makes sense.
PMOS transistors are kind of the opposite. They turn off when you apply a high voltage and on when you apply a low voltage. Huh, okay. Inverted logic, why use both then?
Well, because NMOS logic high equals on aligns more intuitively with how we usually think about digital signals, they're often preferred for building the logic gates within the control system. You know, the parts that make the decisions.
The brains part again.
Exactly. PMOS transistors, on the other hand, are particularly useful for switching power on the high side of a circuit, meaning between the positive power supply and the load. This can be advantageous for efficient power management in certain designs.
So NMOS for the logic, the thinking, and PMOS for the heavy lifting, the power switching.
That's a pretty good way to put it, yeah.
Yeah,
NMOS for the brains, PMOS for the muscle controlling the main valve power.
got it. And there was also a delay circuit involved. What was its job in this system?
The delay circuit. Its purpose is pretty specific: to introduce a set time lag. After a trigger signal comes in, there's a pause before the circuit actually sends out its logic signal to do something.
Like setting a little timer.
Exactly like a timer. They achieve this using a very common combination: a resistor and a capacitor, an RC circuit.
Okay.
When the input signal arrives, the capacitor starts to slowly charge up with electrical energy through the resistor. It takes a certain amount of time, determined by the size of the resistor and capacitor.
Right, the RC time constant.
Precisely. It takes time for the capacitor voltage to reach a specific level. And only when it reaches that level does it activate, say, an NMOS transistor, which then allows current to flow to the next stage, or directly to the load like the valve.
So the RNC values basically set the delay time.
Exactly. You choose them carefully to get the exact delay you need for the process.
Okay, so we've got the power supply sorted efficiently, the isolation keeping things safe, transistors doing logic and power switching, and this RC circuit creating timed delays. That gives us a really good picture of the circuit's architecture.
Yeah, those are the key building blocks.
Now let's talk about the results. They did testing, right? Power consumption tests on all 3 generations of their circuits.
They did. And the results were quite telling.
What did they find?
Okay, so the first generation circuit, the simple relay setup, that used about 16 watts of power.
16, okay.
The second generation circuit, the one that first introduced the step-down voltage idea, that managed to cut power consumption down to 10 watts.
Better. A decent drop.
Definitely. And the third generation, the more advanced step-down circuit using the single signal, that reduced it even further, down to 9 watts.
9 watts. So basically similar to the second gen, but maybe simpler to control.
Roughly similar power savings compared to Gen 2, yeah, but achieved with that simpler single signal input, which is an advantage.
Yeah.
But still, a significant drop from the original 16 watts, nearly half.
Yeah, that's a clear improvement in energy efficiency as the designs got more sophisticated. They also ran tests looking at the fluid flow rate, right? How was that affected?
They did. They needed to see if saving power came at the cost of performance.
How did they set that up? What did they actually measure?
For the flow rate test, they used a system with pressurized nitrogen gas to push water through a pressure relief container and then through their solenoid valve. They then simply collected the water that came out in a measuring cup to see the volume over time.
Straightforward enough.
And what was really key with the third generation circuit was that they could now adjust 2 things independently. That initial excitation time, how long the high voltage push lasted, and the holding voltage the lower voltage used just to keep the valve open.
Right, the fine-tuning controls. And what were the key findings when they started tweaking those settings?
Well, this is where it gets really interesting. They found they could lower the holding voltage way down, all the way to just 8.8 volt.
8.8 from the original 28.
Yeah, just enough voltage to physically keep the valve's internal plunger from closing. And it didn't really change the amount of water that flowed through in their tests.
Wow. Okay, so holding it open takes way less power than initially opening it.
Exactly. And similarly, they found they could shorten that initial excitation time, the push, down to a mere 35 milliseconds.
35 milliseconds. That's incredibly short.
It is. A very brief initial pulse of higher power. And again, shortening it down to that minimum needed to actually open the valve didn't cause a noticeable difference in the total water collected.
So by carefully dialing in those parameters, a really short initial power burst and a much lower sustained power level, what did that do to the overall energy use when the valve was actually controlling flow?
Okay, get this. By using those optimized settings, the 35 millisecond excitation and the 8.8 volt holding voltage, the actual power consumption in a flow system with a water pressure of 5 bar dropped dramatically. It went down to only 3 watts.
3 watts, seriously, down from the original 16.
3 watts, that's an enormous reduction. To put it in perspective, they managed to cut the power usage by over 80%.
Incredible.
Without significantly changing how much fluid actually flows through the valve, at least in this setup. That's a huge win in terms of efficiency.
Wow, okay. From 16 watts just to hold it open down to 3 watts in operation with these optimized settings, that's the kind of efficiency gain that really matters. Did they check if this worked under different conditions, like different water pressures?
They did. And as you'd probably expect, they observed that higher water pressure resulted in more water being collected per cycle. That makes sense.
Sure.
But importantly, those optimal driving parameters, they found the 35 meters excitation and 8.8 V holding continued to work effectively across a pretty wide range of pressures, from 5 bar, which is relatively low, all the way up to 45 bar.
So the settings were quite robust across different pressures? Good. What about the control signal itself? They mentioned testing the duration of the input pulse and how often it was sent.
Yes, they looked at the weak current input signal. They found a direct linear link between the pulse, basically how long the control signal told the valve to be open, and the amount of water collected.
Which makes sense. Longer open time, more water.
Exactly. Pretty intuitive. When they looked at the signal frequency, how many times per second they open and close the valve, they found the sort of sweet spot for their system. Yeah, for the most efficient water collection in their particular setup. The ideal operating frequency was somewhere between 1 and 10 hertz, so 1 to 10 cycles per second.
And outside that range.
If they went The valve doesn't have time to fully open or close properly, and if it's too slow, well, you're just not cycling as often.
Okay, so there's an optimal frequency range too. And finally, they even look at temperature, didn't they? How temperature changes affected the valve coil's response.
They did. They checked how quickly the solenoid valve's coil reacted to the electrical signal across different temperatures. Interestingly, they found that the coil's response time, which was very fast anyway, around 20 microseconds.
Tiny.
Yeah, incredibly fast. That response time didn't really change significantly, even when the temperature varied quite a lot. From a cool 20 degrees Celsius, like room temperature, up to a pretty hot 100 degrees Celsius boiling point of water.
So the valve's basic electrical responsiveness seems pretty stable, regardless of typical operating temperatures.
That's what their tests indicated, yes. Stable response time.
Okay, so let's try and bring this all together. What are the major takeaways from this whole research effort? What are the key conclusions we should remember?
Well, I think the primary conclusion is pretty clear. For this specific type of solenoid valve, at least, using a step-down voltage strategy doesn't noticeably hurt the fluid flow rate,
Right.
but it allows for a really significant reduction in the power needed to operate the valve. That's the big one.
And the third-gen circuit was the winner there.
Yeah, the third-generation control circuit is clearly the most energy-efficient design they tested, dropping that operational power consumption from the original 16 watts all the way down to just 3 watts compared to using a basic relay. That's huge.
Definitely.
Also, the fact that they included those two adjustable resistors, the variable resistors, in the third-gen design is really important
Like that.
because it allows for easy, stepless fine-tuning of both the excitation time and the holding voltage. This makes the circuit potentially adaptable to different types of solenoid valves or different fluid systems, allowing you to dial in the settings for the best possible energy efficiency in various situations.
So it's not just optimized for this valve, it's potentially customizable.
Exactly. Adaptability is key.
And in terms of innovation, how does this third generation circuit stack up against the existing technologies, the PWM and the dual supply methods?
Well, the researcher pointed out a couple of advantages compared to some existing patents they reviewed. The third-gen circuit achieves this significant power reduction and meets the operational requirements using just a single power input and a single simple square wave input signal.
Which simplifies the control system.
Right. And furthermore, their specific choice of using a high-side control transistor, that PMOS we discussed, helps avoid some of the extra voltage drop and associated wasted energy that can happen with certain other designs, like those that might use voltage divider resistors on the output stage. It's a more direct, efficient way to switch the power.
So potentially more energy efficient and simpler to implement and control than some existing patented approaches? That sounds like a genuine step forward.
It really does seem like it.
Yeah.
The research clearly demonstrates that by being smarter, much smarter, about how we control the power delivered to even a common component, like a solenoid valve,
Yeah.
we can achieve really substantial energy savings without sacrificing how it actually performs its job.
Okay, well, we've certainly taken a deep dive into this master's thesis today. It's pretty fascinating to see the level of detail and experimentation that goes into optimizing these seemingly straightforward components like a solenoid valve.
Absolutely. It really highlights how much potential there often is under the surface.
It really does, and it makes you think, doesn't it? If we
Yeah.
can achieve these kinds of power savings, cutting usage by over 80% in just a single solenoid valve,
Mhm.
what's the potential if we applied similar optimization thinking to control circuits in all sorts of electrically powered fluid systems?
Yeah. Think about it. Everything from your washing machine or dishwasher at home
Right.
to huge industrial processes, chemical plants, irrigation systems, they all use controlled valves.
So the final thought maybe for you, the listener, what other seemingly simple components out there might be hiding opportunities for significant efficiency improvements, just waiting for someone to apply some really clever control design? That's definitely something interesting to consider.